So I would like to welcome everybody. My name is Máté, Ferenc, Nagy-Egri, and I work at Stream HPC. And first, a few words about us and who we are. We are a software services company, and we develop software solutions in HPC. It's no surprise. We tend to feel most we develop libraries from ground up, but also port existing solutions, and we also tune performance to various architectures. May that be either some commercially available, but we also do projects with custom SoCs and custom hardware to develop software solutions for those. And in the talk, there will be some of the projects which we were involved in recent times. Let's try this one. Okay, then. Speak just a few words about graphics and interconnect technologies, because that is one place where standards rule supreme, or they are widely adopted. And then about the available compute APIs that are in use today and are popular, and some recent changes and advancements in the landscape. So why talk about internode communication? So if one wants to increase the compute capabilities beyond what is available in one single node running one operating system, then some kind of network communication has to be involved. And if one looks at the scientific framework, the dominant standard, which is used to define network communication across nodes. And while there are a few contenders, for example, HPX and Zero Message Queue, which they are more novel solutions, so they are a lot younger, but they do implement their own network communication semantics. And of course, the network stack has various layers, so software, protocol, and physical implementations. But as programmers, we are primarily concerned at the topmost interface which we deal with, which is the software layer, and there MPI is by far the most adopted. And while NUMA architectures exist, which and NUMA covers a lot of ground and does a lot of the so in by NUMA here I mean architectures where one single operating system could address the entire memory of the entire system. And while these architectures exist, naturally there is a limit to their scale, and in the chase to exaflops, NUMA architectures usually don't scale to those sizes. And for a very long time, I'm sure that everybody who is into HPC knows Mellanox and the InfiniBand brand of connections, which are very popular, primarily because of the sheer bandwidth that they can provide. The easy adoptability, it's just a PCI Express card, or sometimes it's even integrated to the motherboard, and the extremely low latency by which InfiniBand endpoints can communicate with each other. And since NVIDIA acquired Mellanox, but also because reach the operating system and the network I/O stack, a lot of other competing technologies and standards have emerged. For example, CXS, CCIX, OpenC API, which are open standards to implement the physical layer of the interconnect, and then the vendor solutions, they are essentially implementations of those standards. But still, the takeaway message is that even though there are various physical implementations and various network protocols which sit on top of it, not just TCP, which is known from Ethernet, but these technologies can use other network protocols as well. As end users, we are mostly dealing with one communication API, which is MPI. And in the graphics industry, a similar is in a similar position in the sense there were a handful of graphics APIs being used, but dominantly there was one proprietary solution from 3DFX, which was the Glide API, and some of the games there even had a Glide backend, and then proprietary and cross-vendor and cross-platform, either platform solutions, which was DirectX, that was specific to a platform but cross-vendor in nature. OpenGL was cross-vendor and cross-platform. So these technologies competed with each other. And if we fast forward to today, but we don't have to fast forward actually today because it's been like this for a very long time, we have a handful of platform solutions, if we look at Metal, for instance, or DirectX, but they are always cross-vendor in the sense that they support all the vendors which are available on that platform. And then there are the cross-platform and cross-vendor solutions. And proprietary APIs essentially don't exist anymore. There was one very short-lived AMD's Mantle API, but that lived only for 1 year, I believe, or 2 years before it became discontinued. So in both the network side of things and in graphics technologies, standards do exist, and they reign supreme. There are no proprietary solutions available, which us as developers would have to deal with to some extent. And the message is that even though that these standards exist, the existence and the proliferation of standards do not conflict with either competition or innovation. So if somebody would say that there is no innovation in the graphics industry, well, that's a statement that isn't true. If we look at just the going by the images alone and the quality and new techniques of developed in the graphics industry, but more on the existence of standards and APIs in the graphics space a bit later. Now, for compute APIs, the situation is slightly different, and if I would say that that the term GPGPU to some extent has became a synonym of CUDA acceleration, and this is just one pet peeve. But if somebody says that we support GPGPU, and that means that we support CUDA. If you look at the asterisk or you open up the article, it means that there's CUDA support in the library which we are talking about, or the technology platform we're talking about. So there is a persistent CUDA hegemony, which isn't by chance, and I will talk about that just on the next slide. So there is a great deal of both market and mind share in how CUDA is the go-to technology when using when wanting for those for that being the default. Like NVIDIA has been a constant pioneer in the domain of GPU algorithms, and they aren't the sole pioneers and investors, but by large, with the largest investment. So if NVIDIA has developers in just about every single domain framework there is, even if it's for developers of libraries to integrate with the acceleration. The CUDA ecosystem has gained a reputation for its stability and maturity in its 15 years of existence. And there is also a wide assortment of performance, turnkey-ready domain libraries that has won the hearts of many scientists. So it does lower the cost of implementing whatever framework we're talking about, not having to deal with the domain libraries because they are readily available. It is a comfortable programming model, and comfortability comes with popularity as well. So it's one after the other, or the chicken and egg, which now exists. And there are partnership programs which provide upfront benefits to those who join them. So this is why CUDA is in the place it is today, even though it is a proprietary solution. So one can only use it on one vendor's hardware. Even though we saw that portability and being able to go between vendors is a key property in other places. So why not compute? Penetrating the market to the same extent as CUDA has. OpenCL is one of the most persistent contenders in this space. And in the domain of GPGPU itself, it has not reached that penetration, which was or has been expected of it. But nonetheless, it is a extremely popular programming model. Partly because of its simple ABI, so it is a C library itself. So it's a runtime library, which if one can talk to C, then one can talk to OpenCL, which is just about any language, any framework, anyone out there. And it has seen popularity not just in the context of HPC, but also custom embedded SoCs, as I've mentioned, AI accelerators, digital signal processors, and there are a lot of OpenCL implementations out there which aren't public or people don't know about it. So if some company makes an accelerator of their own custom SoC, then they will most likely put OpenCL as a programming model simply because it's well known. So they can recruit developers to code for it, and it's easy to implement. So it has seen popularity mostly, or its popularity is greater outside the GPGPU. And another contender which primarily HIP, which is AMD's answer to CUDA. And without quoting the HIP quoting guide, just the important part. So HIP is aimed to be C++ runtime API to develop applications for both AMD and NVIDIA. And you can write code with very minimal changes if you have an existing CUDA implementation. And that is because syntax-wise, they are very similar to such extent that they are mostly source compatible. So it's just changing the names of a few symbols and identifiers, even with macros, for instance. And the CUDA implementation is a functioning HIP implementations for most intents and purposes. And the domain libraries are also readily available. Moreover, they are open source. So although this Like correlation is not causation, and that is an extremely important statement here. If somebody would look at the market capitalization, the stock prices of AMD, in 2016 they launched their GPU Open initiative, which means that they open sourced essentially their entire software stack. So starting with the HIP compiler itself, but also the runtimes, the drivers, and everything. It's completely open source up on GitHub. Anyone can compile the driver, the kernel, the runtime, and everything from themselves and run it. So, and because of this, this is one of the aspects, and this curve is true actually for most big tech companies lately. But one of the reasons why the aforementioned supercomputer in the United States, the Frontier machine, will be using AMD GPUs is because it gives great power to the system administrators and the users of both the users and the system administrators, that they see everything and they have control over the way they like. So in some sense, one could say that HIP is the open source version of CUDA. And yes. But us as end users, we said that when we are developing graphics or thinking in terms of network, we have one API, we implement it, and we're done. We implement our application against one API, and we're done. But what do we do if we have just these two technologies and they are very close? So as I said, that they are almost source compatible, but they're not fully source compatible. So just two vendors, just thinking of two vendors now, we want to target AMD NVIDIA GPUs and CPU architectures. Then how many backends does my application need to have? Well, and in those cases, HPC and everything that the domain libraries, the BLAS library will just invoke cuBLAS and QFFT and the NVIDIA libraries. So HIP is designed in a way that when run on NVIDIA hardware, HIP completely evaporates and isn't even linked to, and it's not used. As far as I know, it isn't even linked to. But it mostly evaporates. But projects usually don't go this direction. If they support CUDA, then they have native CUDA support as well. So CUDA and HIP, however similar, these are two code paths to take into account with two build definitions as well. Now, if somebody does target HIP and they have a working HIP port of an application, then HIP CPU is another backend which is worthwhile exploiting. HIP CPU is a purely C++17 and OpenMP implementation of the HIP programming model and transitively maps cleanly to CUDA. So if anybody has ever wondered that I have a CUDA application and I wanted to debug it or parallel on the CPU, then HIP CPU is a very good way to achieve that. It's just including a different library. Moreover, it's a header-only implementation of CUDA, and any C++17 compiler can compile it. And then just attach an ordinary debugger to it and debug the kernel, stepping through breakpoints, anything that your CPU debugger supports works. And potentially one wants to have a vanilla standard implementation without any of the GPU technologies. So that's 3 or 4 implementations which are just AMD GPUs, NVIDIA GPUs, and CPU implementation. That's a lot of work. 3 build definitions, 3 code paths to maintain and test for. It's a lot of work. And we haven't even accounted for Intel Intel hardware, Intel integrated graphics, and the soon to come dedicated GPUs. It's not soon to come, they already exist, the BGP. So one starts to question, isn't there a better way? And if one wants to minimize the work and the effort, then yes, OpenCL did this 10 years ago. We had one code to target CPU, GPU, multi-vendor, cross-platform, everything. So we did have solutions for this a decade ago. And what has changed since that makes me say that standards will have a greater role, or will likely play a greater role in the context of GPGP and HPC as well than they do today. Yes, well, if I would have to say what's the point of standards, then somebody just looks at this image and yes, what is the point of standards? It's ultimately less suffering for end users, less things to worry about, less things to care about, and there is no great difference in the feature set on what's on the right. They essentially do the same. So standards are a good thing. And now I'm using the newer level of OpenCL consciously. So what has happened in recent times? OpenCL 3.0 was released recently. It is if somebody hasn't heard, it is a reimagination of the API. And what it did is that it builds on top of the widely adopted 1.2 version. So so much so that OpenCL 3.0 and OpenCL 1.2 are source compatible with each other. So no code change whatsoever is required. And OpenCL 3.0 adopts the Vulkan-like have a slim core, which is a very minimal subset of the API and language, and everything else is extensions. And Vulkan has gained insane popularity due to this approach. And OpenCL has gained a great deal of momentum from this decision. So even though OpenCL 3.0 is fairly new, I think it's not even half a year old, or roughly around a year old, and there are readily available implementations from Intel, ARM, Qualcomm, and even NVIDIA. If somebody updated their NVIDIA runtimes in the last month, then they have a 3.0 runtime on their system. So vendors are behind this idea, and since the last year, a little short of a dozen extensions have been already published to 3.0, starting with subgroup support, and there are AI extensions for machine learning operations, APIC operations. There is if somebody looks at the Thomas blog which has recently shipped, then there are a lot more extensions to talk about. Specifically, there is using Vulkan as well, which is a preliminary extension. So OpenCL 3 is it lowers the bar of adoption, and that is what was the biggest problem with OpenCL, that 2.0 and versions onward started mandating features which always there was some feature which was hard to implement for a vendor. So a lot of obligatory features got in, and that's why nobody really wanted to implement it, because there was always one thing which they couldn't do, or if they implemented it, would have performed poorly on their hardware, and that's bad press. So instead, slim core API and everything else is extensions. Ecosystem. So the ICD loader, which loads the implementations, the vendor implementation, big OpenCL, has gained a new capability to define layers. And now one doesn't have to use a library intercept layers and things like that. It's a standard mechanism to load layers, which can add missing features to a runtime. So if somebody's implementation is missing a feature, then it's easy to add a missing feature to an existing vendor implementation, validate the correctness of the user application, trace the application, profile the applications. There are many. It is again something which the Vulkan API has done and is very popular to use various layers, which can be turned on and off at will. The OpenCL SDK serves as is intended to serve as a one-stop shop for developers. So if somebody goes onto GitHub, it's in the Kronos user. Under the Kronos user, there's an OpenCL SDK, which you can clone, and then you get a complete development package. And the initial set of native samples using C and C++ has been awarded to Stream. So it's coming to GitHub near you. And it's likely next week that all the samples will ship. And we applied for this project because we think that high quality SDK to samples and teaching material is very important to the ecosystem as a whole. And we wanted to lend our expertise to the Kronos group to develop the initial set of libraries, and then the initial set of samples, and then more samples to come. And the 3.0 also defines the semantics of how to have layered implementations. So an OpenCL runtime running atop another API. And most notably, the first such implementation is from Microsoft. It's OpenCL on 12. So it's an OpenCL runtime that is running on DirectX 12. So it can be considered as the baseline of OpenCL support on the Windows platform, because if every GPU vendor has to have a DirectX 12 runtime, and as such, they have some baseline which OpenCL cannot go under on Windows. And this implementation is supposed to work in the WSL subsystem, so even in the Linux subsystem, OpenCL and OpenGL acceleration is available. And there are quite a few graphics and compute standards, and each can be layered on top of the other. So this is a bi-directional or a matrix of mappings, and it does to some extent introduce the n times n problem. So vendors are still encouraged to implement the APIs and have first-party support for it, but layered implementations is very useful to provide baseline of support for all of these technologies, and also to fill in the gaps of platform support or vendor support if there is a gap in some place. And in this diagram, SQL implementations aren't noted, but what are SQL implementations? SQL is another Kronos standard, I would say slightly less known than OpenCL, but that will change fairly soon. The SQL 2020 has been recently released. It is the newest version of this standard. What is it? It's a single source programming model similar to CUDA or HIP. So you write, it's a C++ API. So it's you write one source code which has both the host side and device side code in it, and you compile it, and it will run on a wide variety of hardware. And this is the current set of known and public SQL implementations. The top one, DPC++, is Intel's implementation, and it supports everything which all kinds of Intel hardware, CPU, FPGAs as well. So here, because Intel is invested in both FPGAs, graphics, CPU, and they have this one API initiative, which translates to write one code and run it on a wide assortment of hardwares. And the power of their implementation is that it's also open source. It's up on GitHub, and because there is a great momentum behind SYCL, CUDA support has also been added to the DP++ implementation of the Intel LLVM implementation. It can run on NVIDIA hardware as well. And there is a HPC implementation, which by its name would mean that it's then it has gained CUDA backend as well. It has a mature CUDA backend, ROCm backend, OpenMP for CPU, and it even has an experimental backend for level 0, so it can drive anything which is Intel hardware as well. And it can do so from a single binary, which is again very important that I compile my application once. I don't have to compile it again for other architectures. And Tricycle, NeoSYCL are NeoSYCL I know slightly less about. Tricycle is the implementation of Xilinx, so it's an implementation targeting FPGAs. And Compute CPP is the only conforming implementation which conforms to the previous standard, SYCL 1.2.1, which runs on top of anything which is supported by OpenCL and knows Spear or SpearV, so they can ingest intermediate languages. And the new standard is behind SYCL, and it's increasing in popularity quickly. And how so? Just recently, GROMACS has released their newest version, which officially deprecates their OpenCL backend, and they are looking to replace it with a SYCL backend. As we've seen that SYCL supports just about the same number of hardware, which and the kinds of hardware as well, not by chance, which OpenCL did. And one could say, like, what does one read from this information pair? One could say that it's a loss for OpenCL, win for SYCL. But I would argue that the read for is that the Chronos standards for compute have reached a state where actually projects can choose the technology which makes the most sense to them. So SYCL, by its nature and by its compilation model and everything, is more similar to CUDA. So if a project has a mature CUDA implementation and extensive CUDA support, then going to SYCL makes more sense and is less of a work for that project. While there are other projects which don't want to deal with the C++ ABI and a C ABI, and just that it's a C runtime layer and not a language, but it's just a runtime, makes more sense to them. So if .NET, they do it via the C ABI, and they will not be compiling C++ source files because it's much simpler. So because there is no one-size-fits-all, there are actually standards and technologies to choose from, and that is a big statement. And so there are places where OpenCL SYCL cannot or can't, and there are places where SYCL will go, where OpenCL could, but SYCL is a better fit. And again, these two standards aren't even competing with each other, but they support each other. And only require OpenCL runtimes. So the code is formulated in SYCL terms, but then anything which runs OpenCL executes it. And because there is interop between, one can invoke something written in SYCL from an OpenCL application, and vice versa. So in SQL applications can invoke existing OpenCL libraries. So how can one catalyze the adoption of both of the technologies, not just one or the other? Having a breadth or widely available open source algorithm and domain libraries is important. And for one such library, for example, is AMD's RockPrim, which the development of RockPrim is spearheaded by Stream HPC, as is RockTrust and HipCub. They are the hip ports of the RockTrust and HipCub. They are the hip ports of these two libraries, Trust and Cub. But the implementation of both of them is wired into RockPrim, so there's only one algorithm library in the RockM ecosystem, and RockTrust and HipCub, they are thin wrapper APIs around them. And if somebody wants to look at how these libraries are tuned for one architecture, well, not just two architecture, but the GCN and the RDMA derivatives, how to implement high-performing parameterized implementations of scans, reductions, and whatnot, then they can look into it because it's all open source and even contribute. Domain libraries, BKFFT, which by its name means that it's a Vulkan FFT, but actually it has CUDA and OpenCL backends as well, and it's extremely performant, and it even beats the vendor solutions, both QFFT and WFFT in many cases. Intel's 1MKL is an assortment of libraries, domain libraries, and all of them are open source and formulated as SQL libraries. Most of them are implemented in SQL. And the existing CL math libraries, so the CL BLAS, CLFFT, which were developed by AMD and have been in maintenance mode for the past 5-6 years. They are still extremely performant to such extent that that CLFFT on AMD hardware still outperforms RockFFT. When CLFFT was written, these cards were nowhere near, so they are not tuned for this hardware, but still the performance is comparable. And porting of the domain frameworks, which is the larger chunk of work, and Stream has taken its share in that and has taken part in both porting and tuning Romax, LambD, EmberMD to HIP, and also OpenMM. So, so there's and there's already a lot available to use in importing these applications. And choice is key. So I'm not saying that only standards should exist, because vendors do need their playground when they can tune the last bolts and knobs of their hardware. So, but in an ideal world, these technologies coexist and both are supported. So the vendor solutions and the standard solutions. So some project cannot afford to have 3, 4, 5, 6 backends to target all hardware, and they can choose a reliable standard solution. And thank you for your attention. And if you're interested in joining the development of these libraries and want to work with Stream, then go ahead.
Thank you very much, Máté. To reach the coffee break, but it's time for a couple of quick questions, and you can also ask this.
So, are there any plans to expand this ecosystem in the web as well? Because I seem to remember that many years ago there were some attempts with FCL, and also I see some standardization attempts with compute as well. So, how
I missed the most important word. Extend it to what?
Web. HTML5.
To the web. Yes. aim at bringing Vulkan level of support to browsers, or the Vulkan feature set to browsers. But as far as I know, the API is slightly different, but one can read up on it, the exact details. The primary concern with the because web tech or graphics technologies are a lot more restrictive on what you can access, primarily by not having pointer support whatsoever. As soon as you introduce pointers and you can do pointer arithmetic, that's a big attack vector. And that's what browser vendors weren't really happy about just when they implemented OpenGL ES back in the day, like the WebGL. And they said, okay, now we want to do this with pointers enabled. And then the browser vendor said, yes, we don't need to do that. So I would not expect to have compute grade support in browsers, but anything which can be compiled and translated to compute shaders can work. And in fact, the big feat of OpenCL on 12 is they do this. So OpenCL on 12 compiles code with pointers, C++ code, mind you. And they can transform it in such a way that it conforms, that it's a version of DXIL, which is without pointers, and DirectX 12 can execute it. But there is a lot of footwork in the compiler to erase all pointers.